I think
well, good morning. What I thought we would do is begin where we began yesterday with a statement that the entire seismic processing chain can be derived from one single starting point. And we showed a set of applications early on in the seismic chain of wave separation methods for separating the reference wave from the scattered wave and to do de-ghosting. So let's quickly review what that was about, and then we move to another application, which was a wave prediction form that also derives from some very close relationship from that single equation. So I think it's important because we do a lot of different things in this group. We do pre-processing, wave separation methods. We do multiple removal. We do depth imaging with the velocity. We do depth imaging without the velocity. Yes. How does this sit in some one picture? Yes. These are not separate things that fly in the window and one comes in the door. In fact, they're entirely and totally understandable from a single starting point. And that's a very useful thing to have, to understand where exactly these different techniques separate. Okay? So, I guess we're looking for it. Here's an eraser behind it. So we started off with, can everyone see the lights? We started off with a story like this. We said, imagine you have some homogeneous, K is omega over C0, some world where there's a direct Dirac delta source sitting in an entire universe which is homogeneous except for one localized point source. Localized in space and time, it explodes, and if you look at what happened physically when it explodes, it sends a wave out. And there are infinite number of solutions to this differential equation, and that's a very important one of them being the causal solution, what actually happens physically when the wave explodes. There are many, we found the erasers. Okay, thank you. So that's one statement. Then we said there's another equation that if you can solve this equation, you can solve another equation, which is this equation, where this rho is an arbitrary function that all you have to assume about rho is that when you multiply rho by G0, that you can integrate it. So that covers a lot of territory. And so among the infinite number of solutions of this equation and the infinite number, we start by saying, let's focus on our interest in this being a physical solution. That when the energy source that creates this field ignites, a wave is generated and it interacts with the medium, and what actually physically happens, we call that the causal solution of this equation. The one we care about. And it's very important to understand that no seismic method assumes that the field is anything but causal. Because we use different Green's functions, as you'll see in a second, for migration, but the field is always causal. We're never assuming the seismic wave field is anti-causal. The seismic wave field is what happens when an actual physical source occurs, yes? Now, if you use an anti-causal Green's function in a Green's theorem, what that does is it takes the physical field and says what that physical causal field was previously, okay? By using an anti-causal Green's function. The anti-causal Green's function is anti-causal, but your wave field isn't, okay? It says physical in your predicting it in different locations or taking it back in time and so on. It's just the way you want to relate it at one place in space and time to another. It could be useful for the auxiliary function, the Green's function, to be causal, anti-causal, or otherwise. Yes? So a key point, why are we talking about this? There was a bunch of activity yesterday including wave separation methods, early in the processing tree, and then a step into an important ingredient within Claerbout 3 imaging, the prediction of a field. What would a receiver record inside a volume if you had measurements on the boundary of the volume? Yes? That's, again, so that was all covered yesterday. So we'll quickly review that. We're not going to go through all the detail, but give you some what happened yesterday, and then what is happening today from the same starting point, yes? So if this is what you're after, then you connect this to the causal, and then in terms of this causal solution, this, you can get the causal solution to the actual physical field that you're interested in, not this idealized localized source field, as some RS, if there's a source, is an integral, and the rho could be a function of RS and omega, G0 plus R prime omega dr prime. You integrate over the entire universe, and you get the field that corresponds to this source at any location in the universe by a sum, a weighted sum. This is what an isolated source does at a point R prime. This is now the weight at R prime. Yes? So you take a weighted sum of causal solutions. Why weighted sum? Because this operator is linear. Okay? This is linear elastic wave theory. If you had a nonlinear a wave near the source, this falls. Yes? Nonlinear doesn't satisfy superposition. You understand? Okay. So that's a very important point, and we gave some simple examples of what rho was. In a very simple case where we characterized the velocity as 1 over c0 squared of r is 1 over c0 squared. Just again, a very simple case to exemplify what rho could be. We found that on the one side you had del squared plus k squared p, and on the other side you had k squared alpha p plus a of omega delta. Let's say if you had a source signature times the location of the physical source. So this would be an example of a rho. Okay, so what it says is, if you want to know the field everywhere, you got to know what rho is everywhere. You got to know alpha to know alpha, and C0, which you need for G0, then you know the velocity everywhere. And this tells you that you have to know what created the field. Where was it and what was its character? So you need to know everything about the source in sources of every variety in the universe in order to know the field everywhere. Okay? And that's a modeling method. That's a modeling technique. Okay? And there's nothing I know that violates that. There's no theory that I know that says if you want to know the wave field everywhere, you must know all the properties in the world. Okay? You have to choose a model type, and then within a model type you have to tell me the properties. Then I can tell you the field, whether it's finite difference, finite element, or this. This is not finite difference, finite element. This is perturbation theory, a way to provide, but it's still asking for all the information. There is no exception, I know, to that rule, that to model a wave, you need to know first, you need to tell me the properties of the source, you need to tell me the model type, and then you need to tell me the detail of every model type. Scattering theory does not have a different view of that, okay? Okay, so then we did some, we said, okay, if you want the field everywhere, you have to know information about the whole universe. Let's say I'm not interested for some reason, I have a local interest. I only want to know the field inside a volume. You might think that if I only want to know the field inside the volume, I only need the properties in the volume. That's not true. Because just because you are interested in the field inside a volume doesn't mean the field is only interested in the properties there. The field goes everywhere. You happen to be interested in its properties inside a volume. That's not the field's concern. It cares about everything it went. You happen to be interested in this. There has to be a way that the properties outside your interest can have an expression on the field inside your interest. And that's what Green's theorem gives you. So we had another expression which was a compromise. It says, look, if you want to know the field inside a volume, if you want to know the field everywhere, there is no compromise allowed. You must know all the properties. Yes? If you want to know the field only in a restricted region, then there's a compromise. You must integrate the rho, which has all the properties of source and characteristics of the medium, G0, plus a surface integral of P grad G0 minus G0 grad P. That George Green brought, which, as we said yesterday, this is evolved from Isaac Newton, yes? What is going on? There's a replacement of a surface integral. A volume integral is being replaced by a surface integral. Isaac Newton says you can integrate over an interval and replace it by an antiderivative of the function on the boundary. That's incredible. And when you think about it, right? You have a function which all I need to know is the antiderivative, and then I evaluate on the endpoints. Yes? When you think about that, that gives you divergence theorem, gives you this. This is another way of saying it gives you the equivalent of having the for the field in the volume. It gives you the following. The first interest we had, first of all, a very important statement, extremely important, is that this will give you the physical field inside the volume for any G0, any solution. There's an infinite number of solutions of that equation. This, why? How do you rationalize it? Think about how you derived it. You derived it by assuming del squared G0 was minus k squared G0 plus delta. That's all you assumed, nothing else. Okay? It's a mathematical relationship. It's not like a linear superposition of elementary causal, that kind of rho G0 plus everywhere. It has a very different origin, and that different origin gives it a tremendous flexibility, which we exploit. So among the infinite choices of G0, one is we can choose this to be G0 plus. If you choose it, it's right away clear that we can make a comparison with this, with the guy which is the field everywhere. The field everywhere is an integral on everywhere, rho G0 plus. The field everywhere expression must have G0 plus. It comes from linear superposition of elementary sources, yes? So if you want to make a comparison of this with this, you must have the G0s agree, yes? Once you have that, you can say, well, this is the field everywhere. Among everywhere is, this gives you the field in the volume. Now you pay a lot of money for that, yes? You pay more than you need. You need, for this, to get the field in the volume, I have to have the properties everywhere, yes? But it still will give you that, and so you get two expressions. One is the field everywhere, including in the volume, is equal to an integral over the volume, rho G0 plus an integral over the universe minus the volume of rho G0 plus. And this is valid anywhere, including, this is R in the universe. Anywhere is this, including in the volume. You have another form which is only valid in the volume, which is integral rho G0 plus that surface integral. Yes? If among the infinite choices of G0 here, you pick one to allow you to compare, yes? Then you have a G0 plus here, and then for R in the volume, this is equal to the surface integral. Okay? Okay, so that gives you all these wave separation methods, because then you have a way to have this integral gives you the contribution to the field P for R in the volume due to sources outside. So it's a wave separation due to sources outside, not due to all the sources. So if you want the sources due to the Earth, due to the air guns, you can separate, is the point. So that's where P0, PS, that's where deghosting, separation methods come from that, always with a G0 plus. Clear? Because you're making a connection, this to this. Now you come to a totally different application, wave prediction. Wave prediction goes back to some earlier story here. But you don't need this. If you're only interested in wave prediction, if you're not interested in making a comparison between this and that a whole space form, yes, then I can pick any G0. So let's say I want to predict the field for sources and receivers on the Earth's surface. I want to say, what would the receiver be in the Earth? Why? Because in Claerbout 3, that's what it's about. Predict from surface measurements, what would a measurement be in the Earth, yes? So I want to be able to predict P inside a volume. I don't need it, that P, to be predicted in the whole universe, just enough of the volume so that I can locate a reflector, so I can make an experiment there. So there's something I need that's known, and then there's some unknown. I'm looking for the onset of the unknown, that reflector that I don't know until I image, yes? Clear? So you're looking for the ability to predict a field inside a volume. So if we assume that the source that creates the field is out of the volume, and if we assume that our reference, C0, is the actual, then in the volume, alpha will be 0. If this is actual. So C0 could be variable, yes? But alpha is the difference between what I choose for reference, whatever that is, and actual. If I assume that in the volume, the reference chosen is actual, then that rho, the rho, this will be 0, and if the source is outside, that will be 0, and then you get that, you get for the field for P in the volume, you get only the surface integral with any G0 you want, yes? So then you have a volume and you want to predict the field in. Then we argued that if you have an upwave, then if you choose a G0, which is G0 anti-causal, you need the measurements on top and not on the bottom. Because even if you had them on the bottom, they wouldn't contribute, okay? For a one-way wave. The new thing that we have done is, what if you don't have one-way waves in that medium, yes? Then you have to, then causal, anti-causal, no combination of causal, anti-causal will make that bottom surface removed. That was my first thought, that it would, some kind of going up, the anti-causal will not need this and the down, so it doesn't, you can't arrange it. You have to pick a Green's function such that it and its normal derivative both vanish. In other words, so that that surface integral component on the bottom doesn't contribute. That's it. So whatever your reference medium is, which we'll assume is actual in migration, we must find a Green's function that satisfies that it and the normal derivative vanish. What's the difference between that and, let's say, when you're doing finite difference on the field? Every finite difference method, without exception, has boundary conditions. Absorbing, Al Reynolds, different directions. This places a condition on the Green's function, yes? Not on the field. The Green's function is made to vanish along with its derivative. That's totally, there's no physics to that. That's not physical. We don't care. What we want is that there's no condition on the field, yes? You're predicting the field without the kind of burden that finite difference gives. What are you going to do on the boundary? So you put something convenient and unphysical on the Green's function, which makes no condition necessary on the field. And you're doing modeling, if you like, predicting. So that's a way to understand what happened yesterday. Then the progress in that our students reported yesterday in the wave separation, just to summarize, if you have to sort of write a quick summary, is two real major news. One is for onshore wave separation, yes, for both removing the reference wave, which will have the ground roll, yes, separating that from the reflection data, which is an open question now. Today they do filtering, yes? We're talking about predicting the reference wave, predicting the scattered wave without injuring either one. That Jingwu showed that there's a reasonable approximation that only requires the displacement, multi-component, and we have to, as Kaman said, what if you don't have it? We have to see. It'll be something less. Does it give you anything of value? The question is. And in addition, you need the source signature. Yes, the source signature at the. So that's a significant reduction from needing displacement and traction. Yes, and so that's very important to report. The other is, if you're trying to do these wave separation methods on a non-horizontal surface, ocean bottom, land, you can now do that directly on your own data, yes, without having to predict some effective data removed above it, yes, as long as you know the shape, which you can often on land and ocean bottom, yes. So those are the big newsworthy items from yesterday. So now what we're going to do is we're going to have the same exact starting point, and we're going to do scattering theory. Scattering theory and inverse scattering theory, they're all space. In other words, for example, when you do internal multiple, that algorithm, it doesn't do stripping. It doesn't do like you might be migrating and then migrate, through a volume. It takes every first order internal multiple, no matter what the depth is of its generator, and it attenuates it all at once, at all volume, yes? It's not a restricted, let's do something in a volume. And the reason is that its starting point, this is its starting point. This is the starting point, right here, okay? And so what happens is, you go and you put, so what I want to do is, let's make the source, in other words, I'm going to map this, what we had, into a set of slides that are typical mantra for scattering theory by adjusting this a bit. I want to make this field P idealized in the sense that what I wrote for A of omega delta, yes, I'm going to make A of omega 1. So the P will be a Green's function for the actual Earth, rather than a field that had a source signature. Understood? Yes. So that will make the rho, this guy rho will be 1. Yes? That's step 1. So when you have a Dirac delta source, you call that field a Green's function. Okay? So this becomes a G if I make this a 1 and keep this. Understood? Okay. So now we're in a world of G and G over here, yes? The P's got replaced with G, and we're going to keep alpha, yes? And then what we're going to say is the following. We're going to say that we're going to call the difference, in other words, we're going to define a reference operator, which here is like del squared plus k squared, and L is del squared plus k squared times 1 minus alpha, yes? Omega squared over c squared r, right? Gives you that. And then the difference, L0 minus L, we're going to call that, which is here, L0 minus L is just
in this simple case, k squared alpha. You see? L0 minus L is just k squared alpha. So that thing that's sitting over here is a difference of two differential operators. Yes? This. It grows up. In other words, we're going to generalize and now do the following in these slides. We're going to say, imagine you have an operator L on G is delta, and there's another operator L0 on G0 is delta, where these two operators, one we could call the reference, doesn't matter which you call the reference, and this is some different operator. You can imagine this being reference and this being actual. The mathematics doesn't care which one you call reference, and they're different, yes? The L0 has the properties of the reference medium, and L has the properties of the actual medium, yes? And motivated by what we saw a minute ago, we're going to define an operator V as L0 minus L. That was k squared alpha a minute ago for that simple case, yes? We're also going to define G minus G0 is the scattered wave, the difference between the wave in the reference and the actual. So V represents a difference in operators, which means in some way a difference in properties, and G minus G0 represents a difference in wave field. With this formalism, the equation that we had a minute ago becomes G equals G0 plus G0 VG. Okay? So where did this come from? It came from G equals integral rho G. In fact, this has to be G0 plus. This is an all space solution for G in terms of rho and the reference G0, okay? This equation here is causal, 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 causal. This and this came from the rho. G0 plus on the delta, integrated over all space gives you G0, and the G0 k squared alpha p became k squared alpha g, which became VG, being more general than just acoustic, yes? So this is a very famous equation, which we just derived from that rho G0 plus, yes? This is called the scattering equation, the Lippmann-Schwinger equation. For some, it's the beginning of the world. For others, it's the end of the world. Okay? It's when your mind has to stop. Okay? It's like the no-go zone. Okay? But it is only rho G0 plus is the point, right? That's what this is. All space. So with that, I'm trying to connect what we did yesterday to today. Yes? Okay, so now let's go to the normal slides. By the way, this equation is very old. Max Born was approximating this in 1920. So it had to be before that. Okay? You understand? They called it the Born approximation, the linear when you substitute. Okay, so modeling and inversion. Yes, we'll have some words. Inversion, there's direct and indirect, and we'll say more about that later. If you don't know what direct means, this is the direct solution to that. An indirect solution to the first equation is we'll search. We'll look for x's, maybe real, yes? Missing all the complex roots, yes? But we'll do a search with some weighted of what we want to minimize. LP or something, yes? That's indirect, looking. Direct, indirect. Another very famous direct solution is migration. You give me a velocity that's accurate, I don't need a search. You put in an algorithm and you get the depth. There's no matching, yes? If the velocity is correct, migration is direct. It's not looking, yes? It's not, okay. Now if you don't have the velocity, then things arrive which are indirect. Common image gather, right? And so on. You understand? But the principle of migration itself is direct. It requires information. Given that information, there's an explicit formula for the depth, in particular for C3. So these are indicators of indirect. If you have model matching, objective functions, search algorithms, iterative linear inversion, necessary and not sufficient conditions. Okay? Those are all indirect. The real world, you need both. So before the end of the day, we'll explain what, in our view, the reasonable role for direct and indirect is. In my view, indirect, the relationship between, the balance between direct and indirect is off balance. There's too much indirect. Okay? Part is the computers, we'll just go look. You understand? If we didn't have the solution to the quadratic equation today, we wouldn't have found it today. We'd be searching. You understand? Computational mathematics is taken over from math physics. Yes. Even in the physics department. I'm glad this is being taped. No, because there used to be 2 semesters of required math physics to get a PhD in the physics department. Now it's 1. Yes, 1. The other you can take, but it's elective. You understand? It's diminished and replaced by computational physics, which is very important, but it's the balance between the two is what we're talking about. Okay, so here you have these equations that we just wrote, and here you have this equation 1, which is basically what we said a minute ago, and here's another way to quickly, in terms of operators, if you think of L and G as inverses, if I put this here, and this here, and this here, and this V is L0 minus L, and this here, you can see you get immediately an identity. So there are many ways. So this is a relationship. Equation 1 is not a solution. You have G on 2 sides. Okay? G is on both sides, just like remember we had P equals integral G0 K square alpha P. P was inside, P was outside and inside. You understand? That's the generalized issue there. So people, Max Born and others, they said, let's make a series of approximations. Here you have G is G0 plus this. Let me put in equation 1 on the second term on the right. For G, let's put G0. And then you get this. And then put this in for G0. And keep doing that. Yes? And that you get a series. And that series then becomes a solution, a modeling method. Okay? It's a perturbation. In other words, this says if you want the actual field, the normal way to get the actual field is in terms of L, its actual operator, directly. Finite difference, finite element, lattice-Boltzmann, reflectivity, they're all in terms of actual properties. This is a different way to get the field in terms of what is the field in the reference medium? What's the difference between the reference and actual properties? So this is, this has a G, okay, so this says in order to model a wave field First, you need to tell me model type. I need to know what this L, L0, what are they? It's got to be, I can't put G0 in a computer, or V. I got to have something explicit, yes? So you got to get a model type, then you got to tell me the properties within the model type. And when that happens, then the V and the G0 become specific. So if a very important idea is if you move this on the other side, you get G minus G0, the difference in wave. V represents the difference between some reference and actual medium, yes? Any difference. It says something extremely profound. It says, if you make any change in a medium, you take at one point and change the density by 1/1,000,000th of a percent. Any change. You've changed the location of a reflector, yes? Any change will make a V. If you make a change between L0 and L, which then is V, the change in wave field is always nonlinear to that change. Always. The simplest realization of that is, let's say you have a homogeneous elastic world, yes? And that's our reference. And then suddenly I perturb it, I keep it the same above someplace, and below it I perturb it, making it another different homogeneous elastic half space, yes? I just have a V suddenly, yes? The original field, let's say you have some plane wave coming originally in the L0, it just goes straight, yes? In a homogeneous world, plane wave just, as soon as I put that V there, you get a reflection, yes? That reflection, as we know from Zolpert's equation, is nonlinear to every change, yes? Zolpert's is a simple way to understand you changed a medium from L0 to L, and that change is represented by V, the change in the medium, and the corresponding change in the wave field is always nonlinear. So one thing that this has a structure. This form, this forward form, has a structure. In other words, if I want to use this for modeling, I need L, the actual medium. I break it up into L0 and V. L0 enters through G0, and V enters as itself. Okay. The important thing to notice here is that series is geometric. Okay. If you want to know the difference between our view of forward and inverse and the traditional view of inverse, and I'm not talking about seismic inverse, inverse is the fact that what this represents as geometric is that opportunity is missed. Okay? People think of the forward problem as Taylor series. Yes? Well, in other words, geometric, what do you mean geometric? If you consider, I'm talking about generalized geometric, but this is the idea. If you consider this as A, R squared, and so on. And so it has this form. Geometric series have inverses. You can solve for R. You can solve for R here in this equation in terms of S. You just get that equation is S equals AR over 1 minus R. You multiply S times 1 minus R equals AR, and you solve for R. SR plus AR, and you factor out the R, S plus A, and you get R equals S over S plus A. Or S, yes? In high school, you don't do that. They give you the first term, they give you the rate, you get the sum. It is a little different in that the first term here is AR. Yes? It's starting with this. This G minus G0 is the sum. Okay? So this R is what we just did. S over A over 1 plus S over A, yes? Gives you, assuming all the things you assume about geometric series forms, and those things matter, you get this inverse series. You get the forward geometric series and the inverse geometric series. The inverse geometric series is the inverse scattering series. That's simple. Yes. So what does, if you don't realize that that's geometric, and you think of the problem as this: I have data at M minus data at M0 equals data prime of M0 times M minus M0 plus data double prime of M0 over 2M minus M0 squared. Okay, this is the way people think. And Taylor, there's no, in general, Taylor has no inverse. So what do people do? They say, well, let's look at this. Let's look at this, yes? And then, because they can't invert a Taylor in general, they take a linear and they do this usually with a finite difference, data at M0 plus epsilon delta M, yes, minus delta over, and they invert Frechet derivative sensitivity matrix, yes, and they get this. And then what do they do after that? They change M0. They take the delta M and they add that linear estimate of delta M, and they add it to M0, and they update, because there's nothing that they could do beyond it. You can't invert the Taylor series. You understand? What that form, that initial form that we had says, this is a Taylor series, all right? This is a Taylor series, but a very special Taylor series. It says the thing that people are missing is this equals, you understand? AR squared. All of these, you understand, are equal. Isn't that what geometric says? AR, right? AR squared. So that's a huge simplification, which allows an inverse series, an inverse direct series, just like the forward. You're not doing a linear and updating. The Taylor view doesn't recognize that relationship. You understand? Okay. So, that's one statement. So just like you can call the inverse for R, you could call this that you have S, the sum, you get AR squared, and so on. Here you have S over A. S over A is not R. It's the portion of R that's linear in S. This is not R. This is the portion of R that's quadratic in S. Yes? So it's not unreasonable to call this R sub 1, R sub 2, R sub 3. Yes? This is exactly the linear portion. This is not correcting the linear. This is the quadratic. So you get an explicit relationship for the linear quadratic terms. Yes? And exactly that analog, the V, in other words, the R is VG0. So G0 is just your reference. You're going to have the inverse of the forward series is an inverse series, or V1. This is the portion of V which is linear in the measurement of the scattered wave. This is the, in other words, G minus G0 measured is the inverse. This is the portion of V quadratic, and so on. The question is, how do you find V1, V2? It's a little more complicated than the algebraic geometric, but it's this. You take the forward series, all of the inverse scattering comes from the following. You take the forward series. And the first thing you do is you evaluate it on where you actually have measurements. This business is the field anywhere. We want a relationship between measurements and V. Yes? We want a relationship between measurements of what actually is in your phone and what a reference medium would produce in your phone. In your phone, data. Yes? That's what we want. For the inverse. For the forward, you want to model somewhere else, fine. For the inverse, it's very specific. From surface measurements of the scattered field, we want V. So the first thing we do is we evaluate both sides where you actually have sources and receivers. So this is still a forward problem. Now, if I put in for V everywhere, V1 plus V2 plus V3, where this is the portion of V, linear in the data, quadratic in the data, cubic, and so on. And then if I set terms on both sides of this equation, which are equal order in the data, equal, which you can prove is true, we won't do it here. Okay, if someone's very upset about that, I'll be glad to prove it. Okay, but just accept that for a minute. You get the following equations. You get what is linear in the data on the left-hand side is the data. What's linear in the data? Only one term, the V1. Every other term, V2 is quadratic, V1, V1, quadratic. There's only one term on the right-hand side linear in the data. You get this. Then you go to quadratic in the data. What's quadratic in the data here? Nothing. You get a 0. It's linear. The data is linear in itself. Yes? So your V2 plus G0, V1, G0, V1. This plus this with a 2 and a 1 and 1 must be 0. That gives you this equation, and so on. Yes? Making terms on both sides of the equation, equal order in the data, equal, give you the set of equations. The message that this set of equations communicates is we are the first, I would say Stoll to myself, are the first to understand what it's communicating. Yes? And how different it is from linear iterative. Okay? Linear iterative you saw a minute ago, right? I need to update. I take m minus m0 and get a new m0 and do it again. That's a new Frechet derivative. This guy does the following. It says, to get V1, if you're getting V1, you invert G0, G0. And if that's homogeneous, the background, that inverse is analytic. There's no numerics. It's like a Fourier migration to get V1. So to get V1 requires your data and reference properties. To get V2, what's on the right-hand side? V1, V1. V1 only cares about data and reference. There's multiplies, data times data, so to speak. The inverse step to get V2 is exactly as it was to get V1. The inverse step, if you're trying to get V2, is, again, a Fourier water speed migration. So there's no updating of the background. So here's the basic message. This procedure says you can get, in principle, we'll talk about practice in a minute, you can get V1, V2, V3 directly in terms of your data and G0. There's no updating of the background. So, and it says in will come data of whatever variety, primaries, free surface multiples, and internal multiples, and out will come V. Yes? There's one small problem. It doesn't work. It doesn't converge. Okay? If you stick all that data in, yes, we tested that. That's not an early with Cavallo and then repeated by Mattson. Tested a simple example, 1D, just put all your data in and give it water speed and see if it produces the Earth, yes? Now for a small contrast, it does. Removes multiples, you understand? The machine does all that and well locates. The problem is the contrast is very small, 11%. The actual speed has to be only within 11% of water speed. That means the inverse scattering series taken as a whole is completely and utterly useless, okay? Practically useless. So people who are studying that, you know, whether it's in a U of H and other groups or in California, they need to understand that, okay? The benefit came, well, so we were disappointed. Why? Because it's multi-D and it's direct. And taken as a whole, it's valueless. We thought, can we, if there are tasks that are being achieved, so for example, when a long time ago we studied Goupil inversion, you know, Goupil stripping, when you have perfect data, it works perfectly. It will give you the impedance as a function of depth. It's doing stripping. But when we put in noise and band limited data, it didn't. Okay? But we noticed very early in my career in oil that when you put band limited noisy data, it didn't give you impedance or location, but the multiples in the data went away. I said, well, that's interesting. Something's working here. Yes? The whole deal is not working, but something's working. So that was just a data point. We came to this, and at the same exact time, we were hearing that multiple removal was a problem. Yes? Not from our research colleagues, from ARCO operations people who were furious and telling us that radon wasn't working. Okay? Our researchers there were saying it solved the multiple problem. Yes? And that was a big wake-up call for me, to see operations people screaming, literally screaming, livid with anger. Don't you tell us it's working. You know, we go where you say there are no multiples, and we drill into nothing because there's a multiple there. Yes? You know, so there's no reflector there. So that was a big wake-up call for me, and decided, can you locate where the tasks that we would assume a direct machine would do? Can you locate where free surface multiple occurs here, internal multiple, depth imaging, and so on? Whatever you take out of this, whatever pieces you take out of this for specific tasks, always depend on data and G0. So, free surface multiples don't care about subsurface information. Internal multiples don't care. It's even more than that. The free surface and internal multiple algorithm, they don't care about anything about what model type. Tell me something about the number of parameters in there. Yes? It says I don't need to know. Directly in terms of an operator. Yes, they work. That's how model type independent. The internal multiple doesn't care about what Earth model type. Jingwu showed absorptive, yes? She put in data from an absorptive Earth, dispersive Earth. She gave the reference as water speed with no dispersion, yes? And the internal multiples were attenuated, meaning the exact time and approximate amplitude. Now it's on to eliminate, yes? Again, with no information. So that's Q compensation. Jose Eduardo Lira and Chris Innan found a subseries of this. In comes data that suffered Q, yes? Out comes data without, as if it never had Q, yes? You can see the data. And it doesn't know or need to know Q directly in terms of water. It's mind-boggling to me, okay? I'm in awe of it. It isn't, we don't figure it out. We go in here and ask it, how are you doing that? Yes? You understand? You tell me, go figure out how you're going to remove absorption without knowing the absorption. I don't even know, I couldn't imagine where to start. Yes? But it's in that. Understood? Same with depth imaging. So this is an entirely different view of the world. And there are places on this earth with mathematicians and theoretical physicists where what I just wrote is some kind of heresy. Okay? It's just some thought that you're not allowed to entertain. Okay? It's very heretical. Yes? It's just math. Yes? It just collides with their current view of things. Yes? And becomes problematic. And as I mentioned yesterday, when you're solving problems that are difficult, you have two problems. And I don't have to repeat what those problems are. One is the problem itself. Okay, so that's all this story. So here's an amazing thing. And you'll see some examples of this afternoon. There are two kinds of nonlinearity, because this is talking nonlinear. One is what we call intrinsic. These are words we made up. Intrinsic means if there's something in the world you know and something you don't know. As long as there's something you know and something you don't know, you're going to have some nonlinearity. Zolperts, if you want. Yes? You follow? As long as there's something you know and don't know, there's some nonlinearity. So the only way to remove intrinsic is to know everything. As soon as there's know and not know, you have intrinsic. You understand? The only way to remove that, I have to know everything. Yes? There can't be a place know and place don't know. As soon as you say don't know, that relationship is nonlinear, intrinsic. There are other nonlinearities that we call circumstantial. For example, if you know the velocity to a reflector, that's linear to get the depth, migration, yes? If you don't know the velocity to get to the reflector, to find the depth of that reflector is a nonlinear process, okay? The series does things, yes? But I don't need to know the properties of the whole universe to get rid of that. I just need the velocity to the reflector. That's circumstantial. So the amazing thing is the inverse scattering series deals with both, but it deals with this very differently. If it's possible for you to give information that would be accurate, that would remove that nonlinearity, it decides whether there is an issue or not. So, for example, when you see this depth imaging work of Professor Fang Ru and Simon Shaw and other people in our history this afternoon, you give it some velocity. The first step it does is it migrates as we migrate today. And the next thing it does is it takes that migration and it lets it talk to itself. It's data times data. Now it's migration times migration. And in that communication, that first quadratic term determines whether the information you gave it in any given image is adequate or not. And it lets you know where it's adequate and where it isn't. And where it is inadequate, it calls on terms in the series to act. And where it's adequate, it says there's nothing to do. Another is the internal multiple. Let's say you only had an ocean bottom primary, and you go and you compute internal multiples. By the second integral, you get 0. It says you don't have an internal multiple. It doesn't just start computing. It determines, is that issue there? Yes? Okay. So the one it doesn't is free surface. See, for anything below the measurement surface, the inverse scattering series is going to have its own attitude about what you say. Above it, it doesn't have the wherewithal. If you say there's a free surface, it takes you on your word. So, for example, you'll see in a minute, when we do multiples, if you give it a single primary and you put it into a multiple removal, a free surface multiple removal algorithm, it assumes that there are free surface multiples. You understand? It is buying that there's a free surface. It knows that can't be alone. Yes? And you'll see what that does. So if you, for example, had one primary and a deeper primary, And let's say the deeper primary interfered completely with the shallower free surface multiple. So all you saw in your data was the shallower primary, yes? The free surface algorithm predicts the free surface multiple from this, yes? And subtracts it, which is exactly the invisible primary that you didn't have. You understand? It can't say, well, you know, you're wrong. There was no free surface. It has to take you on your word for above. Below, you say this is the velocity. It says, well, we'll let you know how we feel about it based on what we see in the data. That's amazing. You know where that comes from? One word, direct. Every term in the series has a purpose. It's not perturbing, it's not searching. Every term has some purpose towards one of these tasks. Okay? That's our job, is to locate these terms that are useful. And so how is it that we're taking these subseries and they're convergent and the whole series diverges? Yes? The reason is there are terms in the series that try to do more than one thing. Free surface and internal, and depth imaging, yes? And AVO. We never take those couple tasks, terms, and our view is that they must be the origin of that divergence. There's something in there doesn't add up, you understand? And all the isolated tasks, free surface by itself, internal, depth imaging, nonlinear AVO, those isolated tasks have in each case been convergent. So the ones that are non-isolated must be the trouble, yes? Which we never touch. We never touch them. Okay, see where's the rest of this? Yep. Purposeful perturbation. So this is the tree. Free surface multiples. What it does need, it needs the reference wave out, needs ghosts to come out. So here's a simple cartoon deriving the free surface algorithm. You have a unit comes down, unit wave, up comes R of omega. This assumes that there's no free surface here. So you have a 1D Earth, and you send a unit pulse and a train. This is a train of events consisting of R of t would be primaries and internal multiples. Understood? A train. And then this is the corresponding situation where there is a free surface, the same 1D Earth, assuming some unit pulse, and up comes a wave. Now this has primaries and internal multiples and free surface multiples. But notice, this wave is down and this wave is up. We've assumed that the reference wave is out and we have deghosted. Okay? Deghosted means we're looking at the field that went down from the source, not went up. And the same on the receiver side, yes? So this is deghosted data consisting of primaries, internal, and so what we're going to do is we're going to derive this from that. And then that will give us a way to derive that from this. If we can take this data and produce that, we've removed free surface multiples, because that data doesn't have them. Yes? The data on top. Okay, so you're going to see how, you can see here the essence of what goes on. So there are two things required in this derivation. One, that it hit that air-water boundary with a -1, and the convolutional model. The convolutional model. So the convolutional model says, if I send a unit down and up comes R of omega, let's say, then if I send A of omega down, a wavelet, then what comes back is A of omega, R of omega. Yes? Convolutional model in the frequency domain. Yes? If this produces this, then this down produces this. This times that. Clear? That's all it takes to derive the free surface algorithm. -1 and that. Okay? That's interesting, yes? Because convolution is very general, yes? Okay. Convolution assumes linear. So, what we say is, this unit pulse goes down, and up from what this is deriving the free surface data from the data without free surface. Okay? So a unit goes down, and out from the Earth comes R of omega, which is a train of events, primaries and internal multiples, heading north through the water column. They head north, hits that -1, turns around with a minus sign, and that whole train enters the Earth as minus R of omega. Yes? This train of events in the frequency domain can be considered a wavelet. It's like A of omega. Yes? Understood? So if 1 produces R of omega, then this going down, instead of 1, produces this times what 1 produces that coming out. Yes? Convolutional model. And again, this hits the free surface, turns around with plus, and on and on. So what you do is you add this and this, every other one, because this is downgoing. We're talking about R sub f is, we're after de-ghosted data, yes? We're after measurements of upfield. This would be a downgoing event at a receiver, you understand? As it goes through the water column. So when you add R minus R squared and so on, you get this. And then if you solve for R here, in terms of RF, you get this, and this is the free surface algorithm. R sub f of omega is primaries, internal multiples, and free surface multiples that have been deghosted. You put that here, you multiply by, it's data multiplied by data. That's inverse, that's the simplest incarnation of inverse scattering kind of activity. Where's the water bottom coming in here? Nowhere. Doesn't care where the water bottom is. Is the Earth acoustic here, elastic, absorptive, dispersive, anisotropic? Doesn't care. It cared about 2 things, -1 and the convolutional model. You're getting some sense of how different this is than model matching, yes? How do you do model matching, model type independent, yes? If I wanted a model of multiple, yes? What model do you want, yes? The acoustic, you understand? So this inverse machinery is not model matching. So let me give you, as I mentioned a minute ago, a simple example of that. We can skip this. Here's an example of an invisible primary. Here's one primary, here's a deeper primary, here's a free surface multiple, yes? Let's say we arrange this primary and this free surface multiple to be exactly canceled. Now, this is a little, we actually need to put the source and receiver depths in and so on. I'm just keeping it simple, yes? And so we can arrange for this time to be this time, and we can arrange for this amplitude to be minus the amplitude here, which has transmission and so on. So let's call the amplitude of this event R2 prime, because it has this transmission. Here it has R1, R1, -1 here. Make them equal and opposite, so they cancel. So with what I just said is what is up there, and then your data, this is your data. That's all you see in your data, because these 2 cancel. Yes? So you take this and you put it in the free surface algorithm. You understand? So you take this one, this is all you see in your data, a primary, the first primary. You put it in the frequency domain. It says RF. You square it and add it to itself. Yes? When you do, you get this and this. This is the second primary. It recovers the primary that was invisible. Yes? In other words, you talk about move-out differences, you know, stacking, FK, radon. This you can't even see anything. Move-out differences they look for, yes? It shows you the difference in what's going on. Okay, this is the grown-up version of the free surface algorithm. Carvalho, a student when I was a professor in Brazil. D prime represents deghosted data, and this algorithm is free surface multiple elimination to different orders, yes? This is not SRME. I mentioned this yesterday. SRME does not have this factor, Q. Q is this. This formula will predict the exact time and amplitude of free surface multiples at every offset. SRME doesn't. Okay? It doesn't produce the correct time and amplitude at any offset, in fact. Okay? And it has an angle-dependent error. When does it matter? If you give me a free surface multiple, which is isolated from other events, I will choose SRME. Let me repeat what I just said. If you have a free surface multiple that's isolated from other events, I will choose the Delft procedure over this. Why? It's cheaper. If you get rid of that, things occur, you can implement this in X omega fast, okay? And then you just do an adaptive to deal with the issue, you understand? If you have an interfering free surface multiple, yes, with a primary, which can occur, and the data we're looking at, we will talk about this afternoon, we won't show it, from PGS, or offshore Uruguay has free surface multiples interfering with primaries, yes? So we're going to look at what difference does this make when you don't want adaptive to cause issues, yes? Understood, yes? So it's a toolbox issue. You're going to pay more for this, but the you're going to get amplitude fidelity at all offset. Do you need adaptive with this? Of course you do. You just need less. Okay? Of course, adaptive is the indirect. We need a different criteria, not energy minimization. But you always need some adjustment for the real world issues that are not in your physics, and they're always there. Yes? It's just our PGS colleagues were saying how gingerly they had to put that adaptive on when they had that interference. We want to reduce that burden on the ginger application, okay? If you want, yes? By making the prediction stronger, then the subtraction has less burden, yes? Okay. So here's the internal algorithm. Another student, Araujo, when I was a professor there, this is cubic in the data. Data. This is with water speed migration. It's a Claerbout 3, a Stolt extended Claerbout 3 water speed migration. There are two reasons that this algorithm is standalone capable today. One is it doesn't care about subsurface information. The second, which we never mentioned because I couldn't imagine any other kind of migration, is this B1 migration is that Stolt extended Claerbout 3, which can accommodate specular reflection. It can accommodate when you have a curved boundary, when you have diffractions, when you have head waves or sub-events, yes? That's part of what this interest is in what we're looking at to do this for heterogeneous, is we understand the value that this provided to the algorithm. The form of water speed, so it looks for a deeper, shallower, deeper image with water speed in your data and combines them. The real internal multiple is real deeper, real shallower, real deeper, yes? This works on assuming that if the real internal multiple is really deeper, really shallower, really deeper, then its corresponding water speed images will be still deeper, shallower, deeper. Not in the right place, but in that relationship. That's the reason the reference velocity doesn't matter, because that's going to change their actual water speed depths, but as long as they keep the deeper, shallower, deeper, it works. Okay. So this algorithm doesn't care about subsurface information, it doesn't care about Earth model type, and it doesn't care about reference speed. And as I mentioned, that was a big shock when Bill Trageset showed us Paulus Terengi's Kuwait data, and I said, what was the reference? And he said, water. I would have thought you would need some near-surface properties on land. Reference, and then perturbation. So that's how we understand that, yes. And that's been applied in Saudi Arabia when they do it, it's with water on shore. Okay, so I think this is just showing you a result. In fact, Paulo was involved when he was with us on this data from Brazil with Andre Ferreira, Ricardo Rosa. This is extremely complicated offshore Brazil. Focusing, free surface have come out already. There's a layering here, complicated layering. Okay. So this is one, and the conclusion was, the conclusion you hear from many references that I mentioned yesterday, is that no other method can match its effectiveness. So that's wonderful. But the point is that this delivery fails. This delivery of attenuation of internal multiples, which requires adaptive to finish the job, fails if you have interfering internal multiples and primaries. Fails. You can kill the primary. You can kill the target primary with the adaptive. And interfering internal multiples and targets occur very often. Arujo said when she was at Exxon, worked in Middle East data, it seemed that every primary in the Middle East had an internal multiple. Sort of came along with it, Each one had at least one internal multiple sitting on top of it. So that's not a rare or once in a lifetime. And North Sea Total data, layered, very simple velocity, but the multiples are sitting on top of the primaries. And so they published that and mentioned that they hope this group will do something about it. So there's a bunch of activity here today about doing something about it, yes? To do something that has a less dependence on adaptive, yes? Elimination of internal multiples, not attenuation. Okay, I think that's the end of that. Okay, maybe we'll take a break. Okay, thanks.